So welcome to this video on group theory. This is video 1 on my journey through the book Algebra and Geometry. I would like to welcome you on board, and let's get going with learning about group theory. And group theory really forms the core of the book. But to get to group theory, we are going to start with kind of like the bedrock of all bedrocks of mathematics, which is a tiny few minute discussion about sets. So we mentioned that we're going to be talking about groups today, but to get to groups we have to start with something more fundamental. Now this fundamental thing also lies behind functions. It lies behind the construction of the real number line and therefore standard arithmetic. And this fundamental object in mathematics is called a set. Now a kind of way to think about a set is just a list of things. So when you're going to get food for the week from a supermarket, you might write down a list of items: bread, milk, eggs, so on and so forth. And that list is an example of a set. Now unfortunately, unless really specified otherwise, the order of elements in a set doesn't matter. So although when we usually write a set, we usually write the elements in an order because it would be very hard to read the elements in the set if we put each element on top of each other. The order is just to separate the elements so we can see what the elements are. So a set of A, B, C is the same as the set of C, B, A. The order of the elements doesn't matter. And when we want to say that something's in a set, or something is an element of a set, which is a more kind of common way of saying it in maths jargon, we use a symbol that looks like a E rotated. So this symbol here is saying that lowercase x, so our element x, is in the set capital X. Now we tend to use the lowercase to represent the element and uppercase to represent the set the element may or may not be in. We also are going to define a very particular set called the empty set. Now the empty set, firstly, when I define it, it's going to sound really useless, but it does have uses. So firstly, to define it, the empty set is just a list with nothing in it. It's an empty list. We can formally define it as, if we consider two sets A and B, we can think of a way of combining or getting a set out of those sets as looking at the difference between A and B. So the difference of A and B might be the lists, so the set of elements that are in A but are not in B. And using that idea of the difference between two sets, clearly the difference between a set X and itself is going to be a set with no elements, because if a element is in X, then it can't not be in X. So when we look at X and think about what elements are in X but not in X, we don't have any elements that fit that criteria. So we get the empty set. Now you might wonder, why invent the idea of an empty set? What is the point of a list with no items in it? Well, it's important because the empty set plays a similar role to the idea of zero in standard arithmetic. So just as, if you're doing things like, counting, the number zero might not sound very useful. Nonetheless, zero is a very important number in mathematics. When you're solving equations, often factorising and setting things equal to zero is a good first step. The notion of zero is very useful indeed. And that's because, well, there are multiple reasons. One reason is that zero is the identity element of a set of real numbers that form a group, with the operation being addition. Now, exactly what an identity element is something we'll come on to in a little bit, but zero is very important. And similarly, if we want to define certain groups in terms of sets, it turns out that the empty set acts as our identity element. So if we're doing kind of algebra, or we're looking at equations involving sets and operations between sets, the notion of an empty set is incredibly useful in a lot of cases. And now to look at different ways of combining sets together, so different operations between them. And it's important to consider these because sets are something that comes up all the time in mathematics, whether directly or indirectly. So this notation is very important. So if we have two sets, T and F, the intersection between them is defined to be the list or the set of elements that are in T and in F. The way I remember the symbol for intersection is it looks like the N in the AND, which connects the first and last letter of AND. So that's how I remember the definition of the intersection. Well, at least the symbol for the intersection. The union, the symbol for the union, I remember through thinking of the first letter of union, being U, and the union of two sets T and F is the set of elements that are in T or in F. And importantly, for elements that are in T and F, we don't doubly count them. So for example, if T is the set AB and F is the set BC, then the union of T and F is ABC. It's not AB, BC. So we don't doubly count elements that are common to both sets. And you can therefore think, really, because of the not double counting thing, of the union of T and F being equal to essentially writing a list with all of the elements of T, all of the elements in F, and then subtracting the intersection to make sure that we're not doubly counting elements that are common to T and F. So those are the kind of two standard ways of comparing sets, but we also mentioned earlier the difference between sets, so I've got a diagram here to show it. Now, importantly, clearly the intersection and the union between T and F, these are commutative operations. So the intersection of T and F is the same as the intersection of F and T. It doesn't matter the order of the letters in relation to our operation. However, the difference between two sets, so A/B, clearly that depends on, well, the result of that depends on whether A is first or B is first. If we look at our diagram, we can see that A/B is going to be clearly very different to B/A. So the difference is an example of an operation that is not commutative. If we want to get a commutative version of it, we can introduce something called the symmetric difference of two sets, which you can kind of think of as all the elements of A-B combined with all the elements of B-A. So we see that when we're dealing with sets, there are some operations that are commutative, but there are some which are non-commutative. And it turns out that the idea of an operation being commutative is actually quite restrictive. And a much more general property an operation can have is an operation being associative. Now, almost all operations in maths are associative by nature. There are exceptions. One exception, for example, is octonion multiplication is not associative. And there are other examples as well. But now we're going to look at how we can add restrictions to a set and add restrictions to an operation which combines elements in a set together to get another element in the set. And those restrictions will lead us to the definition of a group. So a group is a very special kind of set in conjunction with a very special kind of operation. And so that's, jump into the definition of a group. So a group is a set, and with a, characteristic capital letter to represent the set. And along with the set, we've got a binary operation, so an operation between two elements within the set. And this operation has to have these properties. So firstly, if G and H are elements of capital G, then when we combine G and H together through our operation, which is partially defining our group, we end up with another element which is also in G. And this is known as the axiom of closure. It means that our binary operation is capable of, jumping between elements in our set, but we can't use it in conjunction with the set to get an element that is outside of the set. And this leads to the operation essentially allowing transformations within the set, but always kind of, after so many transformations, returning back elements to where they began, ultimately, at least for a finite set. And therefore, this kind of closure nature to the sets that form a group means that groups end up relating to symmetry. They relate to, essentially, lots of groups relate to either the symmetry of objects or transpositions, so switching one thing to another. So this idea of closure is very important for the physical application of group theory to things like particle physics, which is very heavily concerned with the symmetry of particular kinds. Now the next rule of our binary operation, if it's forming a group along with a particular set, is that the binary operation is something we call associative. Now, associative is like a generalization of the idea of the operation being commutative. So, there are lots of groups for which the binary operation is not commutative, but by definition, the operation is associative. And really, the reason for this is because if we don't have the associative law, essentially we need to use brackets to be very clear on what we mean. And as we've developed maths in conjunction with the sciences, we want to keep the maths as straightforward as possible, using as little clarifying bits of maths as possible. So if we can avoid brackets, we tend to want to, and that means the operations we tend to come up with are generally associative. So it is rare, though not unheard of, to find operations which have significance within the way that we've built the scientific rules, which are not associative. An example of how general the idea of associative operations is matrix multiplication. So matrices in general don't commute. They're probably one of the least commutative in terms of multiplication, they're one of the least commutative objects imaginable. I mean, with things like the vector product between vectors, the vector product doesn't commute, but A times B is always related to B times A, such that, if you got the result of A times B, you would immediately know what the result of B times A must have been, even if you don't know what A and B necessarily are, providing they're vectors. Whereas with matrix multiplication, if I gave you the result of A times B, but you didn't know what A or B was, there'd be no way of knowing for certain what B times A would be. We can get completely different results. We can, in fact, get completely different even types or sizes of matrices depending on the order of multiplication. So, matrix multiplication is really, really not commutative. However, it is associative, which, given matrices' lack of commuting when it comes to multiplication, I always find slightly bizarre, but matrix multiplication is associative. And then we have our criteria, our kind of third criterion, and that is that within the set there is some unique identity element, which I'll call E. I think sometimes E is called the neutral element. I might be mistaken there, but I generally call it the identity element. And traditionally we always use E to represent it. I don't know why, but we do. Now the identity element has the property that if you multiply a element in the group by the identity element, you get back, the element in the group you started with. And that rule is, commutative in nature. So G star E is the same as E star G. you'll always get back to G. Now, something that is worth emphasising is that the identity element doesn't just depend upon the set, it depends upon the operation that's being combined with the set to form the group. So if you had a set, it is plausible that you could have two different binary operations leading to two different groups, and each of these groups will have a different identity element. But for a single group, there is only one identity element. And we'll actually prove in the next part of this video that there is only one identity element for a given group. Because you can actually prove that statement given our rules about how the identity element operates on other elements, and also, the other rules that the operation has to obey. So saying that the identity element is unique isn't really a statement that needs to be included in the criteria, because the rest of the criteria forces this to be the case, but it's worth putting it in because it's good to emphasise that our identity element is unique, but unique for a particular group, and that does depend on not only the set but also the binary operation being discussed. And then lastly, we have the idea of a inverse element. And the inverse element essentially can be multiplied by the original element. When I say multiplied, I mean combined using our binary operation. It can be combined with the original element to get back to the identity element. And so usually, like if you're wanting to find the inverse of an element of a group, you would firstly find the identity element, and then you can find the inverse of another element. Another thing to note is that if we're looking at our kind of criteria here, then clearly the inverse of the identity element will always give you back the identity element. Now I'll leave that to you to prove, but it's a fun little proof you can do. But what I'm going to do now is I'm going to move on to proving that with statements 1, 2 and 4, as well as how we defined the identity element in terms of the binary operation, we can show that the identity element is indeed unique for a given group. And then once we've done that, we'll look at a couple of examples of groups and solve some problems involving them. So we want to prove that a group has a unique identity element. So we have a group, that group cannot have two distinct identity elements. But to get there in the true spirit of mathematics, we have to prove something else first. Now, maths is often like this. If you want to prove one statement, you have to take a step back and prove an earlier statement that you might want to use. And we sometimes call these kind of mini proofs, these proofs that build up to a bigger proof, we call them like lemmas. So if you see a maths book that have lots of lemmas in place. And it's to make sure that we're being rigorous, or really just being very transparent in the logic we are using. It's something I really appreciate about maths, and maths is incredibly transparent about the axioms at play and the logic behind connecting those axioms. Now, that amount of scrutiny on sticking very rigidly to to precise axioms that's worth saying isn't generalisable practically in many areas of science, but that kind of approach does provide a really strong, solid basis for developing a language, which is hugely helpful for understanding the world and describing patterns, and therefore is very admirable. And so, using this kind of careful walk-through logic, let's first prove something called the cancellation theorem. And the cancellation theorem, or cancellation law, is something you probably used all the time, even if you haven't used it whilst consciously really considering it to be related to groups. Now, the cancellation law is essentially that if we have three elements, A, B, and X, then if A star X is equal to B star X, then A necessarily equals B. And that might sound like an obvious statement. It's worth saying, if we're being very general about star and just calling it an operation, there is no reason why that cancellation should work. But it turns out for a group that cancellation does hold, and let's show this using our axioms of a group. So, this is a statement we are trying to prove. And in the proof, I'll focus on one side of the equation, but if you do a similar process to the other side, you end up with something very similar on the other side, and then we can show that A equals B. Now, to get A or B by themselves, we really need to somehow get rid of the x's, but we can't just, undo the x's on both sides, because that would be assuming the cancellation law works, and we are trying to show that the cancellation law works. So we have to go back to our description of a group and the axioms of a group, and one of the axioms was that if x is an element within the group, then x has an inverse, which is also in the group, and we represent the inverse of x as x to the minus 1. And if we multiply x by its inverse, we'll get the identity element, and something times the identity element is itself, and thus we can make our x's vanish. Now, an important thing to know is that x to the minus 1 is used to represent the inverse of x. Now, in general, x to the minus 1 isn't going to be 1 divided by x. We use the symbol x to the minus 1 because in the case where star is standard multiplication, indeed, the inverse of x will be 1 over x. But in general, if we have some binary operator star which is helping form a group, then the inverse of x will be totally different to 1 divided by x. So it's important not to confuse them. Anyway, if we multiply by x to the minus 1 on, the left-hand side of our original equation, we're going to end up with a star x to the minus 1. Now, I said I want to combine x and x to the minus 1 through our binary operator to get the identity element, and we can do that because of the associative law. Because star is an associative operator, where the brackets are going doesn't matter, so we are free to do that. And that allows us to conclude that a star x to the minus 1 is equal to a, and similarly, if you go through with b star x to the minus 1, you conclude that, the right-hand side of your original equation is b, and consequently, since the right and left hand side of the original equation were set to equal each other by definition, we conclude that A must equal B. So we have shown the cancellation law. I would say if it's not clear the logic behind it, I would recommend pausing the video because we're going to now move on to using the cancellation law to show that a group has a unique identity element. So to get to the proof we were originally going for, let's consider a group G, and let's say that G has two identity elements, E and E prime. Now, if the identity element is unique, then by definition, E and E prime are going to have to equal each other. And we're going to show that this is true. So firstly, we recall that if G is in the group, then G star E equals G by definition. And also because E prime is a identity element, G star E prime is going to have to equal G. Now clearly G is equal to G because an element is equal to itself, so G star E is going to have to equal G star E prime, and I think you can see where we're going. We can say that E is equal to E prime by the cancellation law. Now you might say, well, I'm cancelling G's which are on the left hand side of our operator rather than the right hand side of the operator, but we can prove that the cancellation law still applies using a very similar technique to what we did where we were cancelling a term on the right hand side of our star sign. So we have shown that there is a unique identity element for a group. Now I wanted to put this proof in here, and it's worth saying I'm not going to be doing tons of proofs for these videos, but I wanted to put a proof in here to show how the maths works, and also to give a honest reflection for the kind of proofs within the book. It's worth saying I really like how the proofs are laid out. There are times where, as is done in many maths books, at some point it says something like, as is obvious. There was one where it was talking about whether orbits are disjoint or something, which we'll come on to in a few videos' time, and I was like, really? Well, it's not so obvious to me, and I had to spend a bit of time thinking about it until it became obvious. But a lot of the proofs are very clearly explained. I really like them. And they don't seem, overly drawn out. They seem very succinct. But equally with a healthy amount of words, which I always like. It breaks up the maths a bit. But anyway, now we're going through a couple of proofs. Let's look at a couple of examples of proofs that the book gives. It's worth saying in these videos where I go through examples, that will be me going through my solution to the examples provided. I've gone through my solution a few times, so hopefully my solutions are correct. But if I've done my job well in the videos, hopefully the video will itself allow you to verify whether it's correct or not. But I think it's important to share, solutions, or my solutions from the book. And with it being my solutions, it's also a fair reflection on how I've gone about the problems without a marked scheme to help me, as it were. So, we're now going to have a look at a couple of examples of groups and do some exercises with them. So we're going to have a look at our first example of a group. And this group is quite a nice group because it's a combination of multiplication, addition, powers, and when we bring those operations together along with a nice set, we can form a lovely group. So this is our task. We have a operation star where m star n is defined to be m plus minus 1 to the power m times n. And m and n are integers. So the z is a list of integers. It's essentially like the list of natural numbers, but we're also including 0 as an element within the set, and the negative version of the natural numbers in the set. And so we have essentially a group of both positive and negative integers, including 0, and we want to check that with our defined binary operation star, we have formed a group. So that is, we need to check that star is associative, there is identity element, that there is an inverse element for each element in the set, and then we're essentially done. And we also have to check it's closed, but I'll cheat slightly on the closed part of things. So to discover the identity element, which again I will call E, we use the fact that if we have an element n in our set, then n star E is going to have to give back n, and we use the definition of star to write n star E in terms of more familiar operators. And we end up with the statement that n plus minus 1 to the power n times E has to equal n. And the only way this is going to work for all integers n, so for all members of our set, is if the identity element is 0. So, you know, it won't always be, and definitely in the case of multiplication the identity element is at 0, but the identity element being 0 isn't too rare, mainly because if we're thinking of addition of, let's say, the natural numbers, then the identity element associated with a group involving natural numbers in addition would be 0, because something plus 0 is itself. So since addition is fairly common and the identity element associated with addition tends to be 0, you know, having the identity element being 0 in other groups isn't too rare. So we found an identity element, but we need to check that E star n will also give back n, because remember that was an important property that the identity element had. Not only should n star E equal n, but E star n should equal n. And if you check, E star n will give back n on the basis that minus 1 to the power 0 is defined to be 1. So we've shown that there is a identity element for our set with, you know, the relevant binary operation. We now going to check whether the group is closed. However, I'm going to use the fact that, well, clearly, if m is an integer, then m plus minus 1 to the power m times n is going to have to be an integer. Because depending on whether m is odd or even, m star n is either going to give m plus n or m minus n. But both of those things will give me back an integer, because m and n are integers. And so we can just say we're going to clearly get an integer. So we've shown that there is an identity element. We've shown that our group is closed with our operation. We always get back an integer, and our set is the set of all, well, is a list of all integers. Now, the thing we need to do is to show that there is an inverse element, and to show that our binary operation is associative. Now, proving that the binary operation is associative looks quite lengthy. It's actually quite straightforward, but it's worth saying it looks quite lengthy, and we're going to see that shortly. So we are now going to show that this operation we have is associative, and importantly it's associative providing the inputs are whole numbers. It's an interesting thing to note that this operation is defined in such a way that if we loosen the restriction of the input, so let's say we allow the inputs to be fractions that we can't express as a whole number, then this operation being associative might not work. So when looking at whether something is a group, it's important to consider not only the operation, but the elements who are applying the operation to. So in this group, or in conjunction with the set of whole numbers, the operation we have, which I'll call star, is associative, as we'll show. But as our proof will show, it doesn't really look like star will be associative for some other sets we could easily think of. So if we're going to show it's associative, we essentially want to show if we act the star operation on 3 elements, the order of brackets between 2 of the elements doesn't really matter. So we have to find firstly m star and star k. When we do that, we get this expression, and this is fairly straightforward. The more complicated expression is when we do m star n star k, and that's because when we do m star n star k, the m star n will appear in the power, which we raise -1 to, leading to a more complex expression. So this is what you get, for your m star n star k. And now to show it's associative, we just want to prove if we subtract the first line from the bottom line, we get 0. Now if we subtract the first line from the bottom line, we get this expression. Now it turns out to be 0 providing m and n are whole numbers. And that's related to the idea of if m and n are whole numbers, then -1 to the power of something in terms of m and n is either going to be 1 or -1. So let's look at the first case. So the first case is that the magnitude or the size of m is odd and the magnitude or the size of n is even. Now I'm using magnitude because m and n could be negative numbers. However, in terms of showing that star is associative, that negativeness doesn't really matter, so it's just easier to work with the magnitude of m and n, since magnitudes are both positive. So if the magnitude of m is odd and magnitude of n is even, we get 0, because we essentially end up with doing k lots of -1, -1, and 2 negative becoming an add, so we have k times -1 plus 1, or k times 0, which is just 0. And you can show similarly for the other possible cases. Now I'm not going to show it formally for the other possible cases. I would recommend you doing so if you want to try out the proof. It's sometimes fun to practice things by hand, but also it's very similar to what we've looked at for the first case of the magnitude of m being odd and the magnitude of n being even. So going over the other cases might be a little tedious if I was going to do all of them in this video. But now we've shown associativity, we need to show that each element has an inverse and that inverse is within the set of elements. So often when we're trying to work out whether something is a group, doing the hard stuff is showing that the binary operation is associative, because that tends to be fairly computationally lengthy, like what we've seen. Also sometimes finding the identity element for a group can be tricky. However, once you have the identity element, it's often fairly straightforward to work out what the inverse element is, and to show that the inverse element is indeed also within the group. And that's what we're going to do now. We're going to take what we learnt about the identity element and use that to show that each element of a group G has a inverse G to the -1, which is also in the group. So here is our binary operation defined in terms of elements m and n. Now we're going to work with elements g and g to the -1, but what we have here so far is much more general. Now the special thing about acting star between g and g to the -1 is we get back the identity element. So by definition, in terms of what the inverse of a element is, g star g to the -1 has to equal e, and based on the definition of what star has been defined to be, we can rephrase that as g plus -1 to the power of g times by g to the -1 has to equal e. Now before we found that the identity element was 0, this means that if the magnitude of g is even, and bearing in mind g is a whole number, so the magnitude of g is either even or odd, but if the magnitude of g is even, then g is equal to minus g to the -1. So g is equal to minus its inverse. So for example, the inverse of 2 in our group would be -2. And the inverse of -4 in our group would be 4, and things like that. Now, if the magnitude of G is odd, then a element is actually equal to its inverse element. So for some groups, you can have situations where a element is equal to its inverse. And that can actually be for quite a few elements in a group, depending on how the group is defined. Now, it's worth saying that evidently, because G is a integer but is allowed to be positive or negative, G to the minus 1, as it's either equal to G or equal to minus G, is also going to be within the group. So we have shown that the inverse element of each element in the group is also in the group. So the group is closed with respect to inverses. So really, that's everything we needed to show to demonstrate that our binary operation acting between integer values is indeed forming a group. So we've gone through showing that something is a group, and now we're going to take a slightly different route to applying the maths of group theory. We're going to look at something that we're going to take for granted to be a group, and then we are going to find an inverse element for a particular element in the group and use that inverse element to do some core solving equations, but solving equations where the operation won't be familiar addition or subtraction or other things. The operation will be the operation of the group. So we'll be doing algebra, if you like, within the group itself, and using the operation of the group. So our first task will be to find the inverse element of 2. And this obviously supposes that 2 is in the group, but we've been told that the members of the group are x, where x is a real number, but x doesn't equal 1, and clearly 2 is a real number and doesn't equal 1. And also, whilst I won't go through it formally, one thing to note is that x star y is clearly associative, because x star y is defined in terms of addition and multiplication, which individually are associative, and multiplication is like repeated addition, at least when we're multiplying two integer things. So it's not too surprising that, a combination of addition and multiplication will lead to something that is associative. It's just a side comment, but worth making. That it seems plausible that this binary operation is associative, and therefore, goes some way to explaining why we seem to have a group. But anyway, before I show how to work out the inverse element of 2, I would recommend pausing the video, having a go yourself, trying to use some of the ideas we've talked through in this video, because I don't want to spoil the surprise, as it were, or the fun of solving something yourself. So I would recommend have a go trying to solve it. If it seems really tricky, have a break, try again, and if it seems really tricky after that, don't worry, I've got a solution coming up. But anyway, I'm going to have a go at showing the solution now, so I would recommend, if you want to have a go at solving this yourself, you pause the video. Now, if we want to find the inverse element of 2, or really any inverse element, the first step usually is to find the identity element, and then finding inverses is quite straightforward after that. So to find the identity element, we use the idea that E star y has to equal y for any member of the group y. And this leads to the conclusion that E has to be 0. And that's because this has to work no matter what member of the group Y might be. So we can't set 1 plus Y to equal 0 in most cases. So we've got the identity element, which happens to be 0. It's worth saying the identity element will not always be 0, but in this case it seems to be. And then to find the inverse element of 2, we use the idea that if we have a element G and its inverse G to the minus 1, then G star G to the minus 1 is equal to E by definition. So if we do that with 2, we end up with this expression. Now it's very important to note, we cannot do 2 to the minus 1 times 2 is equal to 1. We cannot do that. And that's because 2 to the minus 1 doesn't mean 1 over 2. It means the inverse of 2. And that's very important to make clear. When we replace letters with numbers, it's very easy to quickly jump back into thinking of minus 1 as how it's defined in standard arithmetic. It's worth saying we are still doing group theory, so we cannot go 2 to the minus 1 times 2 equals 1. We can't do that. And I put that here just to emphasise, and I put that there because when we replace letters with numbers, it's very easy for old habits of usual arithmetic to slip in. So we can go a bit further with our expression for 2 star 2 to the minus 1 by remembering that 2 star 2 to the minus 1 is equal to E by definition. We've shown E equals 0, so 2 to the minus 1 star 2 or 2 star 2 to the minus 1, whatever you like, is going to equal 0. And therefore we can kind of factorise to get 2 to the minus 1 as we did before. Well, as we factorise before to find E. And we end up with 2 to the minus 1 is equal to minus 2 over 3. So the inverse of 2 is minus 2 over 3. Now, you might wonder, what is the point, what is the practicality of finding an inverse? And the key beautiful thing with finding an inverse is it allows us to cancel things from both sides of the equation. So if we've got 2 on both sides of the equation, we can cancel the 2 by using the inverse, so 2 to the minus 1. And we're going to use this idea to actually do a bit of algebra to solve an equation involving our binary operation, our star, as it's been defined for our group. So we've come very far, I think, and our last bit of this video is to solve using what we found out for the inverse element of 2. We're going to show that 2 star x star 5 is equal to 6 and find out what x could be. And it's worth saying, as was before, I would recommend having a go at this yourself, so I would recommend pausing the video. And when you're ready, click play and see how your solution has gone. So I would always recommend when answering anything to write down the thing that you're trying to solve. It makes it easier to refer back to it rather than trying to find it amid tons of symbols in question. Now we want to cancel the 2 on both sides, and we will also want to cancel the 5s. And we can do that using the idea of inverse elements. So clearly 2 to the minus 1 star 2 star x star 5 is going to equal 2 to the minus 1 star 6, based on how x has been defined in the question. And we can use the idea that 2 to the minus 1 star 2 star g is going to equal g, because 2 to the minus 1 star 2 is the identity element, and the identity element star another element is just the other element. And that leaves us with x star 5 is equal to 2 to the minus 1 star 6. Now, it's worth saying one might be tempted to cancel out the 5 by starring by 5 to the minus 1, and you might think it doesn't matter where we put that 5 to the minus 1, like whether it's on the left or right hand side of x. It's worth saying with that you have to be careful, because although star is associative, we can't assume in most cases that star is commutative. It's worth saying in this case star might be commutative. I'd be tempted to say it is, because addition and multiplication are individually commutative, but we can't in general assume that. So if we want to cancel out the 5, we have to make sure we star by 5 to the minus 1 next to the 5, and that will restrict where the 5 to the minus 1 can go. So one way we could do it is by starring by 5 to the minus 1, but actually I realised on my notes, because star is fairly easily defined, we can just jump straight into replacing star with familiar addition and multiplication. And then we end up with this expression, and solving it we get x is minus 11 over 18. Now I've gone through this a few times in my notes, so I'm quite sure that that is the correct solution. I've also checked a little bit insofar as quickly looked at 2 star x star 5 with x being minus 11 over 18 to see if we get 6, and it seems to check out. Now it's worth saying with the solutions, these are my own solutions. I'm pretty confident with the ones I've given. However, as I go through the book and the content gets more difficult, the chance of me making a slight mistake somewhere in my solutions, particularly if I'm trying to prove something and by some fluke I get the proof right, or by, I suppose more likely, a lack of rigour, I still end up with the right conclusion. Well, I'm kind of just ploughing my way through the book as best as possible, but I feel that gives a honest reflection for what it's like to journey through the book, given that the book doesn't have solutions, at least within the book. And they might be online, but I'm not sure if they are, and I know many people probably have the experience of reading maths books without having access to the solutions to exercises, because sometimes the solutions are just not given at all. So in the name of making this as genuine as I possibly can for what it's like going through a typical maths book, these videos are made prior to me, checking the author's solutions, if indeed the author's solutions exist anywhere to be found. But I hope you got something out of this video. I hope it's been enjoyable. It's worth saying this has been quite a bit of pure maths, but I will be linking this maths to other things in my videos on my channel as the channel builds. So I think it's good to have a bit of a mix between pure maths and applying some core maths to physics. But if you've liked this video, I would recommend liking it and subscribing if you want to see more videos like this. Got some more videos coming up on this channel, And I wish you a really good week ahead. I hope you enjoy the sun. Um, yeah, and keep up with drinking lots of water as well. Or hopefully something refreshing. I love apple juice, but that's just me. But anyway, wishing you a brilliant day ahead, and hopefully see you for some more wonderful physics and maths soon.